Everything is ready.
Okay, perfect. Okay, so thanks everybody for joining this last session of the day. I don't know if it's better to say good morning, good afternoon, good night, or whatever, because this is kind of going online in different time zones. So first of all, I would like to thank the co-chair here, Anubis, that joined us for this session. So we will be essentially presenting those two fast abstracts that we have today for this session, starting from Mirko Staderini, which is a PhD student at the University of Florence. He is preparing his thesis, so he is now at the end of his PhD dissertation and preparation of the thesis. So I believe he is more than ready to provide us a very interesting and very keen description of his work. So I believe that Mirko is ready, and Mirko will be presenting a paper which is called Static Analysis Tools Applied to Smart Contracts. So Mirko, floor is yours, or better to say, let's see the video and then we will ask you questions.
Thank you for being here at the LADC 2021 Fast Abstract session. I am Mirko Staderini, a PhD candidate at University of Florence, and I'm presenting the work Static Analysis Tools Applied to Smart Contracts. At first, let me briefly summarize the main point of the presentation. At first, background and motivation, then the paper goal, after that a security evaluation, next security improvement, and I conclude with the main results. I would draw your attention on background and motivations. Blockchain are literally chain of blocks. You can store everything in each block, theoretically. It is used to improve the security in distributed systems. Smart contracts automatically execute computerized transaction while maintaining a synchronous system state. There are main issues, scalability, legal aspects, and the security. There are several platforms for smart contract development: Ethereum, Hyperledger, NAM, Neom, and some other. Ethereum is one of the most used platforms, and it has Solidity as primary and Turing complete language. So it means that it permits to build applications in a lot of different areas, but it also has a problem in the sense that it is vulnerable of attacks. CWE is the most wide used list of software weaknesses. It applies a stepwise abstraction scheme in the form of hierarchical taxonomy. It is used to classify vulnerability-related weaknesses. For example, the National Vulnerable Database of the US uses a slice of the CWE to classify vulnerabilities that comes from the common vulnerabilities exposure, a list of vulnerabilities. So, more than this, static analysis is the most widely used method of code inspection. It requires a low effort, it has an incomplete fault coverage, but it is still sufficient for most of applications. I would focus now your attention on the paper goal. We have seen that one of the most critical points of smart contracts concerns vulnerabilities. So, our goal is to propose a methodology for evaluating and increasing the security of Solidity smart contracts through static analysis tools. Let's now look to the next slides that show the security evaluation of smart contracts. Looking at online resources, research papers, the Solidity documentation, we identified a set of 33 vulnerabilities, and we grouped them in 10 categories based on CWE, and this permits us to abstract from the syntax or language, and to focus on vulnerability behavior. Then we define 9 static analysis tools to use, and each tool has different granularities and uses different rules. Then we have to harmonize that. In order to do it, we identified each control rules for each tool. Then we mapped the rules to weaknesses and vulnerabilities, extracting only those ones that focus on our set of vulnerabilities. And then, before any experiments, we estimated the vulnerabilities that remain uncovered and the categories that remain uncovered for each tool. Next, we had to define smart contracts to analyze. So we extracted 400 smart contracts from Ethereum Blockchain Explorer, Etherscan, through a Java cloner, and we processed it with all tools that we have selected. So what we have found? We found a lot of positives. But at the end, we don't know if these positives are true or false positive. So from this dataset, we extracted 15 smart contracts. 15 means that 9,700 lines of codes. And yeah, this subset cover the most 5 frequent types of smart contracts. For example, game, gambling, bet, and so on. It represents the main features of the contract, so all the loop instructions, for example, the usage of assembler and some other. It represents the vulnerabilities of the reference dataset. It means that it represents the predicted vulnerabilities, because we know that tool predict only positives. And after that, we manually inspect all the line of code, determining the ground truth. And then we could analyze, based on results of the tools, for each tool in this set, true positive, false positives, false negatives, and true negatives. This way, we can build the confusion matrices based on a general evaluation and specific for each category of our classification. So, using the confusion matrices of each tool, we can define some performance indicators as recall, precision, F1 score, and balanced accuracy. Related to balanced accuracy, it permits to analyze unbalanced data, and in fact, in our case, we have that true negatives are more than 90% of the total of our data. So, using these performance indicators, we can analyze how tools are good in what they propose to do, considering only what they can detect, and then we can evaluate the smart contract security using tools as black boxes. Then, let's now move on the next point. In this part of the presentation, I would talk about the security improvement of smart contracts. We want to improve the security of smart contracts, so we try to improve the coverage of tools using a tool combination. So there are several ways to combine tools, and we choose the way in which true positive represents a vulnerable row in which at least one of the tools finds a positive. And accordingly, we have definition of false positive. So this way, we investigate the combination of true, true, and false tool, and we analyze the coverage and the precision, because we increase the true positive with combination, but we increase also false positives. After that, we want to analyze the prioritization of false negatives. So false negatives are vulnerabilities that escape detection. So we identify 2 scoring systems. The first is the CAPEC, based on the pattern attacks, and the second one is the CWSS, that is based on the CWE. We identify types and occurrences of false negatives that escape of the tools combination in our pilot set, and then we compare the two scoring systems. Let's now focus your attention on main results that we found. Considering the preliminary analysis of tools, we found 5 vulnerabilities that no tools is able to detect. Considering the tools that are best built, we saw that Sliter has the overall best performance, and for specific classes, considering specifically the coverage, we have that Securify 2 and Remix have better results. For the best performing tools, we have that Securify 2 is the best for the coverage, and Sliter, considering the precision. For the evaluating the combination, Sliter, Securify 2, Smart Check, and Remix is the best combinations that permit to reach a coverage of 0.9%. And
evaluating the prioritization, we have that CAPEC and CWS identified 6 types false negative critical or high severity.
This quickly brings me to the end of my presentation. We can conclude that real-world smart contracts contain a lot of positives,
in order to analyze it, we extracted a subset, investigated this subset of contracts, and we identified the coverage limit for each tool.
in order to increase the
security of smart
we
contracts,
identified the
best tool combination of our list, and we defined false negative that have to be analyzed first because of the highest priority that I have.
Thank you for your attention. And then, do you
have any questions?
Okay, let's thank the speaker, and I believe we have time for questions. So if there is somebody from the audience or other people, any kind of question related to the work that was brilliantly presented by Mirko, Mirko is there to answer. So any question from the audience? Otherwise, I have a couple. Okay, I will start with one. So clearly, the problem when we talk about security is first, you have to identify if there is a problem. So you have a lot of attention on coverage, false negatives, and all these kind of things that you want to avoid. Now, we know also that whenever we try to lower false negatives, usually false positives go up. Now, this is not really a security problem, it's more a usability, availability, whatever problem. How do you deal with that, if there is a way, according to you, to deal with that? Because I imagine that when you combine many different tools, and you need at least one tool which is, finding a vulnerability, you may have false positives because there is one tool which is wrong and it signals a vulnerability somewhere, while in fact the code is perfectly okay. So what is the step that you need to feel to make this technique of combining tools usable in practice without raising too many false positives?
Yes, thanks, Tommaso, for the question. This is a very nice problem because the best tool, so the tool that has best performances related to the coverage is also the tool that provides really a huge amount of false positives. So at the end, if you want to have the highest coverage, you cannot you have to fight against the false positive. The only thing that we can do is using combination. If the focus is obvious to find the highest coverage, is using combination with this tool that is Securify 2, for instance, with the Sliter that has the highest precision, so that it generates the less quantity of false positive. If you really don't need a nice level of security, but you need a medium if your business is not really totally damaged for vulnerabilities, but you can also think that some kind of vulnerabilities can also be there, so you can also leave vulnerabilities. So the best thing that we can do is use this tools with high precision. So Slider has the second coverage, but the high precision, the precision of Slider is like something 93%. So it's really high. It's difficult to find a way if you really focus really on security, because the best tool has this problem, and yeah, to avoid it, you have to think to analyze a big amount of this line of code. So it's really a big problem in this case.
Okay, thanks for the answer. Do we have any other question which popped up to your mind in the meanwhile? Also try to write in the chat if you need something different than talking. I mean, if someone is connected only listening, you can still type on the chat. Okay, otherwise I have another question. It's more a curiosity. You say that you have 9 different tools. So you run all the tools in parallel, I guess, and then you vote the individual results. Now, did you think also in using those 9 tools in a different way? So maybe use just 3 of them at the beginning, and then only if they say that there is a vulnerability, you scan again the same line with other tools. So instead of running all of them at once, you create some batches, like, I don't know, you run two or three, then you run other 2 or 3, depending on maybe the very precise ones are the ones that you call at the beginning, and then the very coverage-oriented ones are those ones that you find at the end. Also, I don't know if this is technically sound.
No, technically sound is possible. Obviously, we haven't planned it. We haven't done it because our first focus was on the security. And try to improve the coverage. On the other side, it is still possible. The problem is still is the following: you can use the precise one. We know that with the Slider, that is the most precise tool, we leave some vulnerabilities, but at the end, the only thing that we can do is reprocess completely from scratch the contract with this tool. So we cannot process some line. Obviously, we should. We should process all the smart contract, the whole smart contract. At the end, when you process the whole smart contract with the other tool, you find an enormous number of positives, and you really don't know if they are true or false. So at the end, the problem remains the same, I imagine. But we can think about it, and perhaps we find another way to process smart contract and to analyze them.
Okay, so if there are no other questions,
please, one question, a curiosity. Congratulations, Mirko, for the work. Do these tools analyze smart contracts of the other platforms than Solidity, like Hyperledger?
For Hyperledger, that uses you know that some Hyperledger uses Solidity as language, so they can also. It should be we can process smart contract through this tool. The problem is that we don't have to process tool that uses with tool that find gas vulnerabilities, because Hyperledger uses a complete different way for gas instead of Ethereum, obviously, and we could have strange results. For the other vulnerabilities, yes, we not really in a complete way. It's there are some other work that try to investigate with tools, with Solidity tool in the smart contract developed in Hyperledger. And yes, there are some different results due to the different way in which Hyperledger develop and smart contract. Also, if still Solidity. So it's not a complete reply. It's yes, but we should pay really attention to results, because we could have some misleading results.
Okay, thanks.
Welcome.
Okay, so I believe that we could thank again the speaker. Thanks, Mirko. And
Thank you.
then I think we can move to the second speaker. So Anubis, please.
Okay. Good afternoon or good night. I hope everybody is fine. I would like to introduce myself. I am Anubis, I'm Brazilian, and I am professor at Federal Institute Sul-Rio Grandense, Campus Passo Fundo. The next paper is the Reliable Traffic Sign Recognition System, and the authors are Mohamed Atif, Andrea Ceccarelli, Andrea Bondavari. The second speaker, Atif Mohamed, is a PhD student at University of Florence, and he got the bachelor degree and the master degree in Pakistan. Atif is now working on traffic sign recognition through machine learning, also investigating the robustness of the tools techniques against camera failures and under adverse environmental conditions. Now you can see the video, and after we will have the questions.
Hello everyone, I'm Mohamed Atif from University of Florence, Italy, and today I'm here to present about our study that is Reliable Traffic Sign Recognition System. Traffic sign detection and recognition is basically an important part of the advanced driving assistance systems. The aim is to provide assistance to the driver. It helps the driver, and it's useful for the autonomous driving and even for the monitoring of traffic signs for the purpose of maintenance. So incorrect recognition may have severe impact on the safety of society, environment, human, and infrastructures. In addition to the shape and color of the traffic signs, there are many other challenges to recognize traffic sign correctly, such as motion blur, visual camera failures, occlusions, or sometimes physically altering the integrity of traffic signs by people. So this create many difficulties for the recognition of traffic signs correctly. In literature, different machine learning based classifiers and deep classifiers are utilized for traffic sign recognition. The purpose of this study is to propose a robust TSR system against different attacks and failures, as we discussed, like visual camera failures, motion blur, occlusion, or environmental changes, etc. We are planning to utilize generative adversarial networks to corrupt images of traffic signs and investigate the robustness of TSR system. Furthermore, we are currently working on designing a failure detector. The purpose of the failure detector is basically to inform the TSR in advance before recognition whether the images are corrupted by some failure or not. The background is basically the main challenge is to devise such a TSR strategy which is more robust against different possible failures. In literature, there are many TSR strategies that are applied using traditional machine learning or deep classifiers. or even some TSR system process single frame, or there are few studies which process sequences of frames, like they're using sliding windows concept. For the experimentation, we are basically using 3 benchmark data sets, that is Italian traffic sign dataset, German traffic sign recognition benchmark, and Belgium traffic sign dataset. Furthermore, in this study, we explore the robustness of deep classifier for frames that are corrupted by camera failures such as broken lens, dead pixels, and no bare filter, etc. There are different approaches for TSR are applied and found that few camera failures. In our previous work, we applied different camera failures and we corrupted the frames of the traffic signs, and we noted that few camera failures are more dangerous and those failures need further attention. Generative adversarial networks are nowadays very popular to generate perturbated images, starting from a clean set of image, in addition to camera failures and environmental conditions. GAN will also be utilized for generation of faulty images, and we are planning to include corrupted images to the training process through data augmentation. Furthermore, we are also planning to design a failure detector which will work with the TSR system and will notify the TSR system in advance whether there is some failure in the captured images or not. For failure detector, different approaches will be utilized in conjunction with the TSR component. By extending failure injected datasets through GANs, designing a failure detector, and inserting corrupted images during training process through data augmentation, we aim that the proposed strategy for building a robust TSR system, and we will evaluate the robustness of the proposed TSR system. These are different strategies and that how we can utilize a failure detector with the TSR component. So in the first one, if we see, there is input traffic sign and it will pass through the failure detector. The failure detector will give us probabilities against different failures, whether there if the probability is higher for some specific failure, we will decide a threshold, and if the confidence is greater than the threshold that the image is clean, so then we will pass it to the TSR component, and TSR component will basically decide the final output for that specific traffic sign. That will be the classes of different traffic signs. So this is one strategy that how we can apply a failure detector. The other one is we will pass a traffic sign to the failure detector, and failure detector will give us probabilities against different failures, and those probabilities that are given by failure detector in conjunction with the input image will be provided to the TSR component. So TSR component will process the input image and these output probabilities, and the TSR component will finally decide the output class for that specific input image. The third one is the traffic sign is provided simultaneously to failure detector as well as TSR component. Failure detector will give us the probabilities against different failures, and TSR component will give us the probability against different classes of traffic signs. And these two probabilities are combined or merged, and these merged probabilities are provided as input to the one meta level classifier, and this meta level classifier will output the final class again for that specific traffic sign. So these are three different approaches that we can utilize a failure detector with the TSR component. Conclusion: this study devises different strategies for building a reliable TSR system, and we consider different failures that can happen to traffic sign in real life because of occlusion, because of environmental changes, because of camera failures. So any failure that can happen to a traffic sign in real life, we consider that. And we create many faulty datasets starting from public benchmark datasets. We also discuss how to implement a failure detector and how it can effectively interact with a machine learning based TSR system. Furthermore, we propose different ways to implement such detector either as binary or multi-class. The failure detector can be binary, like for example, the image is clean or not clean, or we will use multi-classes. For example, this image is corrupted by this specific failure. For example, broken lens, there is the rain effect, or something that. Overall, we conjecture that the proposed strategy and especially the combination of failure detector with TSR component will result in a reliable TSR system. And we are currently planning to execute the experimental campaign and verify or deny the conjecture that we have that failure detector with the TSR system, component will work better. So in this way, we will make a robust TSR system. Thank you for your attention. That's all from my side. If you have any question, you can ask. Thank you.
Thanks, Mohamed, for the presentation. Now we have time for questions. We have the question of the Nico. When do you think having results of this experimental campaign? The Mickey, Mohamed.
Sorry, thank you. Actually, we have performed some experiments, like we discussed some camera failures. There are some changes from the environments, like for example, there is raining or something that that change happen in the environment. So we considered those failures and we applied those to the traffic signs. As we already discussed, 3 benchmark data set, we corrupted those frames, and we analyzed that there are some failures which are more dangerous. For example, they are affecting the robustness of the classifiers. And for the failure detectors, currently we are working on this, and experiments are going on, and our conjecture is that combining the failure detector with the TSR component will increase the robustness of the classifiers and the TSR system overall. So currently the experiments are going on.
Okay, may I have another question? Do we have time? I believe we have some time. So Atif, thanks for the presentation and for your work. Question is, we don't know the experimental results yet, but do you have a feeling about the 3 different techniques that you presented before? Do you have a feeling about which one is going to be the preferred one?
Okay, actually, we have suggested 3 different approaches for the failure detector, which will work with the TSR component. And currently, we are performing the experiment. So at the moment, I can't say that which one will be performing better. But my feeling is, my overall feeling is that failure detector with the TSR component will increase the robustness of the TSR system. But at the moment, I can't commit that this strategy will be the better one.
Okay, thanks for the answers.
Questions? No. So thanks, Mohamed. I think the subject of your research is very interesting, especially for the purpose of the different ways to implement the failure detector. Congratulations. Thanks.
Thank you. Thank you.
Tommaso, something else?
I don't think so. I mean, also we have the last presenter, which is up in the middle of the night. So if we don't have anything else to say, I believe we can close the session. Thank again the speakers and the attendees. Thanks also to you, Anubis. And
I would like to thank the participants, and we appreciate your presence, and have an excellent event. Thanks a lot.
Thank you.
okay.
Have a good night. Thank you.
So thanks everybody. If there are no other discussion items from the organizers, I believe we can close the session and also the conference for today, I believe.
There's nothing else. I'm closing the session. Thank you.
Thank you.